everyone. Now let's look at another LeetCode question. This is problem 323. Called number of connected components in an undirected graph. Alright, there is an undirected graph with n nodes. There is also an edges array where edges I equals a b. Means there is an edge between node A and B in the graph. The nodes are numbered from 0 to n minus 1, return the total number of connected components in that graph. Okay, so let me reread the question statement to make sure I understand it. You are given an undirected graph with n nodes. From 0 to n minus 1, and then there is array edges given by a comma b. Return the total number of connected components in that graph. I'm still a bit confused on the question, so let's move forward with the examples there. Example 1, n equals 3, and then edges are given 0, 1 and 0, 2. Output 1. Example 2, you're given n equals 6, edges are 0, 1, 1, 2, 2, 3, and 4, 5. So let me draw the first one. It should be 0, 1 and 0, 2. Now example 2, 0 connected to 1, 1 connected to 2, 2 connected to 3, there are 4 and 5 are connected. So output is 2. Okay, so I think I get it. Here we are given... Yeah, so I got confused with the question because it begins by saying there is an undirected graph. Which means that there is only one graph. So it turns out that you are supposed to count how many graph is there in a given input. Okay, so I think I would like to clarify a few things. First of all, the range of n. So how many nodes are there? It's given by 1 to 100. Then let's see what else we need to clarify. We know the edges are full. I think we don't need to do that. So I think that's all that I need. Now I think I understand the problem. Let me think of some possible approaches. On top of my head, I could think of one way. Now what we could do is we check for, we go through all the edges and then we try to find out which part of the which graph that a node belongs to. So for example, let's see. For example, in example 1, see that 0, 1 and 0, there's an edge that connects 0 and 1, meaning that 0 and 1 belongs to a graph. There is also an edge, 0, 2, and we know that 0 belongs to a graph that is together with 1. Now we know that 2 also belongs to that particular graph. For example 2, we see that 0, 1, first of all, they form a graph. And then 1, 2 is connected, so 2 also belongs to the same graph as 1. 3 also belongs to the same graph, but 4 and 5, they form its own graph. Okay, so I think I could just check it this way. Does this sound reasonable to you? I want to start coding, unless there is a further optimization that I need to explore. Alright, so I'm going to start coding. So first of all, I'm going to need a dictionary. And I will do so that I could keep track of which node that it belongs to. Which graph that it belongs to. So in the beginning, I'm gonna check if A or B already exists in the dictionary. If not, then I create a graph for it. And then I'm gonna, let's say I just call the graph as one of A or B when I create a new one. So the next time I see A or B, then I could just assign it to, wait, hold on, I could not just simply do that. How about the edge appear later? And they appear later that they are connected. Alright, so I think we could not simply just check it the way I just described. Okay, let's see what we could do here. So I can do it that way, but I need to make sure that they all point to a particular node as a root. So how am I gonna do that is, I think we are gonna do it by using the disjoint union graph. So basically the way it works is that you're gonna create if A and B does not exist in this set, then I'm gonna assign one of A or B to be the root node. And then in the future, if I found that A and B are actually belongs to a graph, then I will just assign both of them to that particular node. So let me try to simulate it with our example. Example 1, I will have 0 and 1, and then 0 and 2. 0 already there, so we set parent as 0. So there we go, we only have one graph. Example 2, we have 0, 1, and then 1, 2. And then we see that 1 already belongs to a graph, and 2 does not belong to anything yet. So we just assign 2 to the parent of 1. Okay. Now 2 and 3 are connected. 3 we see that 2 is connected. Now we set 3 to have a parent of 0 then 4 and 5 both are not connected, so 4 and 5 we create a separate one. So let me come up with an example 3. Let's say we have 0, 1, and then 2, 3, and then later on we have, say, how about 1 and 3. Now let's work on this. First of all, we have 0 connected to 1, and then 2 is connected to 3. And then how are we going to transform this so that they all belong to the same one? So what I'm going to do is that 1 and 3 are connected. Then I know that the parent of 1 is 0 and the parent of 3 is 2. Okay. So what I can do is 3 I will set it to the parent, which is now 0. So 0, 1, and 3, and then 2. So 2 will also point to the parent of 1. How about there is another node there? So let's say E is 0, 1, 2, 3, 2, 4, and then 1, 3. So 0, 1, 2, 3, and 2, 4. How are we going to transform this into the correct one? I think what we can do is that okay, so we can actually shift up all of the children. And by that, how am I gonna shift 4 to point to 0 then? Okay, how about this? Can I just make use of a list to store the children of 2? And I would need to store the parent then in this case. One, two, three, So how do I make 2, 3, 4 becomes have a 0 as the parent? That means I need to make sure that I know that 4 is a child of 2. So if I create a dictionary to the set, that might work, but I will take some space to do that. How about in the future when I see 4 and I check that the parent is pointing to another node? It means that the parent is not a root node. Then I just switch it to point to the root. Think that could work. Is it possible that this would branch out to more than 4 levels? Yeah, I don't think they could branch out to that high. Because as long as we make sure that the tree is of head 1, then when a parent becomes a child, then the height becomes 2. And then in the future, we just move the child to be pointing to the root node. Alright, I think that should work. Now let me try to code this up. I will use a dictionary. I'm gonna call it parent. Okay, now after I initialize it, I'm gonna go through all the edges. For A, B in edges, if A not in parent and B not in parent, I'm gonna add them. So parent of B equals parent of A equals A. Otherwise, elif A in parent A and not B, then parent of B equals parent of A, and if B and not A, parent A equals parent B. Or it could also be both A and B are in there. Everyone, I just realized that I have been turning off the recording. So you have missed all the discussion, but let's continue from here. Hello everyone. So sorry about that. Yeah, for this question, I accidentally paused our recording, so we have lost all the discussion. But let me go through the implementation once again. The idea is more or less the same, but except that I have changed the implementations for correctness. So in here, I will have the parent, which will contains a dictionary so that I can know what is the parent of a given node. Visit will be used to keep track of all the edges, all the vertices that are connected, so that I know which nodes are not, say, have been checked yet. Basically, they are individual. Or actually, I could just get rid of the visit and then say here I'm going to create a dictionary of I to I for I in range of n. Okay, currently, so this is initializing the parent for each node to itself, and then the child will have all the tag, meaning this tag will contain all the children of a node. Then I am going to go through all the, let me delete the visit there, it is not unnecessary. Actually, I think I don't need this all, is it? We'll try that. Yeah, okay, so then this is the much more concise solution. So here I'm going to have a parent and a child. Of course, parents, there is only one parent for each node, because I am using it to, basically I'm going to have a root that will point to all of the other nodes, and this root will represent the root of a graph, and this graph will have access to all of its child, or all of its children. So when I go through the edges, I don't need this line. What I basically do is, I think I don't need this too. I can delete this. Basically, I will try to get the root of a particular node, and then if they are the same, then I don't need to do anything. I just continue, because it is a sample. Otherwise, I'm gonna set one of them as the parent, and then I will move all the child to the other parent, and also extend the child. So I think I don't need this line too. This line is not necessary. To end that. Okay, let's put it back. Anyway, so parent of B will now be updated to A, and therefore each child of B, I also update the parent to A. Now after, I think I moved it up for better clarity. Yep. So after that, I will extend all the child of the parent. Child of A. I'm moving all the child of B into child of A. And then after I do that, I don't need the child of B anymore because I have moved it to A. In the end, I just need to return out of the number of unique parents there. Okay, so this will give us the correct answer. In terms of complexity, I think this would be something like because we add all the parents and then we move all the child, so the child would be at most O or V. So V is number of vertex, and then we have all the edges. So how many edges are there? It could be n squared. So n squared number of edges. Let me just call it E, capital E, because that's what we usually use. So capital E, and then for each edge, there is gonna be V edges that I need to remove. So E times V. So that is not quite efficient, but I think that's all that I could come up with for now. So I will so this video is pretty short because I have missed all the discussion earlier and I did not come up with this answer easily before. So I think I will make a follow-up video on this as another attempt to this question. So I think we'll stop here for this one. Thank you everyone.